Hello everyone and welcome to this week's video in which we're back looking at SU2 once again. Specifically this time we're going to be looking into parity and how we can understand parity, the conservation of parity, and we can understand why that the weak nuclear force does not conserve it. So first of all, let's sort of look at it more. I don't know. Let's give an explanation as to what parity is. So, in classical physics, we have this idea of if you were to flip a system through a mirror, it would behave perfectly. It would just be flipped. And this sort of symmetry, this idea that the world will behave the same if the coordinate system is flipped over, that's parity. That's this idea. And what has been discovered is that out of our fundamental forces, ignoring gravity, we have, of course, the strong, the weak nuclear forces, and electromagnetism. The strong electromagnetic force, the strong nuclear force, and electromagnetic forces both follow something called conservation of parity. So the idea here was in a time where particle physics was starting to be a big thing. It was useful to define things through numbers like strangeness or charge, or I mean that one had been around for a while, or spin or other stuff. Angular, yeah, spin. And some of these, like I think strangeness is a good example. Strangeness is kind of a hard concept to understand, but at the very least, you know that it needs to be conserved in under all particle interactions, right? So so then they had this number. They had this number parity, and the idea was that the parity of the system had to be conserved in total, and that's the conservation of parity. Um, and so, as I said, the strong nuclear force and the electromagnetic force, they agreed with this law. They followed it. However, in 1956, Chiang Sheng, I'm probably saying that wrong. Cheng Sheng Wu is the important name, did an experiment with the National Bureau of Standards, I think, in America, using cobalt-60. It is a very cold sample of cobalt-60 that is polarized using a big old magnetic field, really cold. It's like 0.05 Kelvin. And then there's a little crystal that measures up, that lights up every time something interacts with it. And then the idea is that I don't want to go too much into the practical, but the idea was to find out if a weak nuclear decay, the beta decay chain from the cobalt-60, if that would have an equal proportion of particles going with some spin on each side. And because spin is a pseudo-scalar value, this allows them to extrapolate as to whether or not this parity is conserved. And it turns out it wasn't. With the reversed fields, there were more, we'd say left-handed or right-handed, so actually there was a bias towards the left hand. And we're going to work out where that comes from today. Let's finally start writing things down, I think. So, as hopefully you remember from last time, we have our Dirac bispinner, which is this, and obviously I've written one thing and I can't write. It's this left-handed and this right-handed. These two spinners we have. Remember the Wahl spinners from last week? It's the same thing here, but we have a left-handed and right-handed Wahl spinner. And those two, these are both two vectors as well, so this gives us a 4-component vector. And we have this this spinner is governed by the Dirac matrices. So we have that, oh dear, gamma to the mu, where mu is 0, 1, 2, 3. And usefully, this follows a Clifford algebra. So if we have this gamma to the mu, gamma to the nu, then this is equivalent. This is equivalent to gamma mu gamma nu plus gamma nu gamma mu, which is just going to give us our Minkowski metric tensor. For anyone who's done QED, that's going to be 2 epsilon mu nu times our identity. So this is our 1 minus 1 minus 1 minus 1 Minkowski metric tensor, and then what is useful is if we take this in the chiral basis, which I think I talked about last week, we actually get the we get these nice block forms that we can use. So it's 0, I 0, and then for the ith gamma it's 0 minus sigma to the I, and 0, where those sigmas are representing our Dirac matrices from before. Let's sort of work out what this handedness means, and we use a special special Dirac matrix. Sorry, these are the other Dirac matrices from last time. The Pauli matrices even. Did I mean Pauli? I believe so. Regardless, we take the 5th Dirac matrix, and this is simply I gamma 0, gamma 1, gamma 2, gamma 3. Of course, because we only have mu defined for 0 to 3, so we multiply by I to get the 5th. And what's an important thing to prove here? Well, this gamma to the 5 squared is I. And that can be shown if we multiply these together. This will be gamma 0, gamma 1, gamma 2, gamma 3, gamma 0, gamma 1, gamma 2, gamma 3. And we can commute our gamma 0 to the left, minus here, because of the 2 i's, because it's anti-commutative. Yes, so then each time we take a gamma 0 to the left, it's going to pick up a minus. So this is going to be minus 1 cubed gamma 0, dot dot dot. Oh, then that's actually not dot dot. 1 dot 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 gamma 3 gamma 1. I may as well write the gamma 2 because the dot is minus. We pull those to the left, and then this is just going to be gamma 0 squared, because that's going to cancel out to be positive, times gamma 1, gamma 2, gamma 3, gamma 1, gamma 2, gamma 3. Now we know what that is from our identity up here. It's just going to be epsilon to the 0, 0, eta to the 0, 0, sorry, times our identity, and that of course is our identity. So this is that's 0, gamma 1, gamma 2, gamma 3, gamma 1, gamma 2, gamma 3. In fact, we can do this repeatedly. Pull all the 1s out, pull all the 2s out, pull all the 3s out, since it's an even number of all of those. That will then be I times minus I times minus I. You can go and work through that if you're interested. This is all stupid maths Clifford algebra nonsense. But we do helpfully end up with that being I. So we can write gamma to the 5 in a nice block form for, in fact, it's diagonal on our leading diagonal minus I and I in the Weil basis. So I think we're fine to move on. It would be useful to also note that, no, I think that's not useful to note because it's just saying that this is anti-commutative with other Dirac matrices, but I'm not gonna, I think it's that important. Now let's look at chiral projectors. So we're going to have two operators. These are chiral projectors or chiral projection operators, and we have PL, which is our left parity, and this is 1 minus gamma to the 5 over 2, and we have PR, which is 1 plus gamma to the 5 over 2. And these need to satisfy 3 criteria. So they've got funny names: idempotency, exclusivity, and completeness. Those being that p squared is equal to p. That's idempotency. Mutual exclusivity is that if the multiple of them is 0, because if one of them is, the other one cannot be. Of course, it can't be left and right. And completeness, which is that the sum of these are both I. These can be proved. I think the only one that is left to be proven, probably out of not so trivial, is it? Oh no, it wouldn't even be. I mean, I'll do it for the sake of. I'll do p sub l squared, and I'll leave pr squared for u. But this is fairly easy. Gamma 5 over 2, 1 minus gamma 5 over 2. This is just going to pull that out, so it's a quarter, 1 minus 2 gamma to the 5 plus, and then it's just difference of 2 squares. No, binary expansion. Thus, gamma to the 5 squared, which of course we already know is I. Or rather, in this case, it will be plus 1, because that's our I, which is then 1, so that's 2. 2 minus 2 gamma to the 5 over 4, of course, is just 1 minus gamma to the 5 over 2, which is PL. And this would also be for PR, squared is equal to PR. Again, it would take not very much algebraic manipulation to see that the multiple of those two is equal to 0. And I think completeness is fairly trivial because the plus and the minus will cancel out. So we're left with to double check that they, or rather, we're kind of aware now of the useful part of these, which is that we can apply them to a Dirac bispinner and receive only the left or the right part. They basically, what they do is we have a 4-component Hilbert space, and they can decouple. It's called decouple the parts of it. So, for example, if we did PL times our, see, these never end up looking good, whereas these ones are much easier to do. Regardless, this is then in block form I0, 0, 0 times L and R. This can be done, but it's going to be that's 0, that's 0, that's 0, which is simply and this is equivalent to only the left part of our bispinner. And this would be conserved if we popped our other eye down there. Now we can start to look at the Dirac conjugate. This is where things become a bit algebraically heavy, which means I may be thinking more. But I will try my best to keep it explanatable. So the parity transformation, importantly, reverses our space, but it preserves time. So if we have some tr, this goes to t minus r. Importantly, this is still t in both of these. This is generated by our gamma 0. So if we do that, and then if we take a translation, I don't know how to draw this letter, because if I'm doing it, I'm just LaTeX it, or I don't really care when I'm handwriting. If we have a parity transformation on it, what we can then say is this is equal to gamma naught times r operator, or a bispinner even, which is 0 I 0 times L and R, and this is simply going to be L and R. So this has done nothing apart from, sorry, I got that wrong around, R and L. There we go, that makes more sense. Apart from the very important thing it's done, which has swapped. You can see where that comes from. That's going to be 0. The top row is going to be 0 plus R, and then that's going to be L plus 0. So this is, I mean, vital. And this is just a combination of our two parities, our two projection matrices rather. So that's great. Now to look at like physical observables, we have to understand this Dirac adjoint translation. So that being, that's equal to here, that's our Dirac adjoint times gamma 0. And we could look at this under parity, or translate this under parity, as I said, through parity. Prime, or dash rather, is going to be that should be dash, the adjoint of that times gamma naught, as by our definition, and this is going to be gamma naught times the bispinner adjoint times gamma naught, which is going to be, we can take that out, so the Dirac adjoint times gamma naught adjoint times gamma naught. And gamma naught is Hermitian and it squares to I, so we know that we will be able to get rid of this. Thus, this yields that I, don't forget that, which is, this is terrible, gamma naught. Useful. To be clear, this is still, I'm not a fan of that. That's still psi dash. So this tells us about our Dirac conjugate here. And now I think we can bring in the weak force and work out where that comes from. We've done all the setup. Riveting. So we have these two currents, and we have a vector current and an axial vector current. This is sometimes referred to as VA theory. So this is going to be our electromagnetic current for the first one. So we have V to the mu, and this is here gamma to the mu, again times psi. No, what are you? Why is there a text box? Go away, text box. No one's been using text boxes since Microsoft Word. No one uses Microsoft Word. And this is going to be sidebar. I realised I missed a load of sidebars up here. I just completely forgot they were in my head. So we need one there and one there, and also obviously one there, and then one down there. There we go, that's much nicer. So there's a sidebar there, except, oh no, I don't want it to be like this. I would like it to be, I forgot to, it's too hot in this room. That's what's getting to me, trust. It's not because my brain's slowly breaking down. So we put this through a parity transformation, and we'll do V to the gamma again, and that's going to be dashed. And that is psi dash, psi bar dash, gamma to the mu, so our Dirac matrix, and then our original. This is our Dirac adjoint of psi, and then this is our original psi dash. And then we can, of course, substitute in stuff. And that's going to be with the bar 0, gamma mu, gamma 0, psi. We can evaluate this component by component for each mu. So for mu equals 0, and that's our temporal component. So mu equals 0. This is equal to V0 dash is equal to V0. And then for any other ith mu, we get, I mean, you can just plug it into that, it's fairly simple. We get that V to the I dash is equal to minus V to the I. And that makes sense. This turns exactly like a classic spatial vector. Wonderful. However, what if we insert a gamma to the 5, the fifth Dirac matrix, and we form something called an axial current, which I'll write like this, and it's here, mu, gamma to the mu, gamma to the 5, no bar on that. Well, now let's work with this, and let's apply a parity transformation on that. Dash. Don't forget that. Mu, just from our definition, but with our dashes, and then this will be gamma to 0, gamma to the mu, gamma to the 5, gamma to 0, there. And we can again evaluate this component by component. However, we will get interesting results. Let's take gamma equals 0, mu equals 0, sorry. And what we find is that this then becomes minus here, gas 0 bar 5 psi, which is minus a to the 0. And for mu equals I, we get that this is the positive, so this is plus a to the I. Oh my goodness, it transforms as an axial vector. This is also the same as transforming as a pseudo vector, which you've definitely come across if you've watched my channel, or to be honest, done anything you know what a pseudo vector is. So this is astounding, because we can then use this in looking into weak current, and in fact let's do it. So we'll look at the interaction Lagrangian of the weak force. So I believe this is a J. It's a fancy looking J. Am I going to be able to do it nicely? No, but can I do it? Yeah. That's alright. That's alright. So this is our weak, and that's to the mu. That's going to be bar, gamma to the mu, and then 1 minus gamma to the 5, as from before, again times our bispinner. This is gonna do good things, mu boom boom, because those gonna go away, or rather expand. And we already know what happens with that and what with that, because this is v to the mu minus a to the mu. Wow. This is our weak force interaction Lagrangian. And we can perform a parity transformation here and see what happens. So weak again, mu via our parity transformation goes to v to 0 minus a to 0 minus v minus a, and this is v to 0 plus a to 0 minus v minus a. This is an absolutely catastrophic result. I've written catastrophe in my notes. I think it's quite funny. The Lagrangian of the weak force does not transform to itself or its negative. The relative sign between the vector and the axial vector components has completely flipped. So we actually have this v to the mu minus a to the mu transforms to v sub mu plus a sub mu. That's our translation here. So what does this mean? Well, our Lagrangian of our universe, with our weak force, or rather the total Lagrangian, contains this v to the mu minus a to the mu term, but it does not contain this v sub mu, or rather v to the mu plus a to the mu term. That is not involved. And this sort of shows that we have a completely different set of rules, and this, in fact, it's so vital that I'll box it. This idea of parity doesn't exist for this weak force, and we saw that it exists with the, or rather, I showed over here with the vector current, here, that it does in fact hold for electromagnetic current, but when we go to an axial vector current or a pseudo vector current, like the one that is governing our weak nuclear force, it does not hold under a parity transformation. Now, this was discovered by Wu in 1956. This is vital because quantum electrodynamics and quantum chromodynamics, that being the studies of the strong force and the electromagnetic force. Those utilize the pure vector currents that preserve parity. But the weak force has this chiral V minus A. This is where we get the VA theory from. And under a reflection of space, the sign here flips entirely, which renders the weak force absolutely, catastrophically parity violating. It's been a long half an hour of some heavy algebra, but I hope you have enjoyed this. And I don't know, it's been really fun looking at sort of abstract uses of abstract algebra and SU2 especially. But yeah, maybe I'll can be bothered to find something else to do on it next week. Or maybe we'll do something different. I don't know. I'll see you then though. Goodbye.